Okay, this lecture we're going to talk about electric flux. So we're going to review with review the electric field and drawing electric field lines, and then we're going to get into the flux, the definition of flux, and how it deals with closed surfaces. If you remember, we create a point charge. We create a charged area, a charged item, and then we put point charges around it, and we draw these lines that are lines of force. These are the vectors, the continuous vectors of force as you would move away from this particular charged particle. So if you placed a test particle along those lines, the force would, that's the direction of the force that the test particle would experience. And so that field, just as we would have newtons per kilogram in a gravitational field, here we have newtons per coulomb as our field here. Now, as the lines become less, as we get less lines in area, the electric field gets weaker, which should make sense that as they get closer together, we're closer to the point charge. With 1 over r squared should be increasing our force as we get closer, and as we move further away, it's getting weaker. Now, electric flux then is the amount of field lines through a cross-sectional area. But we've talked about this before. Isn't the number of field lines arbitrary? That if you're drawing the electric field, you can draw as many lines as you want, so long as you're proportional with all of your field, with all of your charges within your drawing. All right. Now, the electric flux, the strength, this does not mean strength of field. It does not mean strength of field. So, we're going to draw 2 parallel fields here. We're going to draw one with our charges really close together. Okay, and so the field for this is going to be, we always go from positive to negative. And if you remember, that's because we're putting a positive test charge in there, and it repels from a positive and attracts to a negative. Okay, and then we do another one where the charges are much further apart. All right, and this is going to have field lines like that. Then we're going to take a cross-sectional area of this. Okay, so if we imagine we take, okay, this is intended to be drawing in 3 dimensions here. Okay, and here's our area, and if we take the same area, and I'm going to try and draw the same thing, or at least the same size. Okay, pretty close. That the number of lines passing through this particular area is greater than the number of lines passing through this area. If they have the same area, then we have more lines passing through the denser field. Yeah? Okay, that's a way of talking about the line density, and it's kind of a way of thinking about flux, is the line density of the field. Okay, now, this is a weaker field, this is a stronger field, because the lines are closer together. Yeah? We're good. Okay. So let's describe the density of these lines. Well, our electric field I'm just putting the absolute value of it because we're just talking about the strength of the field, regardless of whether it's a positive or negative charge. Okay, is equal to the amount of flux. Remember, flux is the amount of field lines through the area. So this, for example, we would have 5. Okay, now remember, it's arbitrary. We're just talking about relative sizes. If this would be 5, this would then be 3, right? So there's a greater flux through this area than there is through this area. We're just counting the number of lines. All right. So our electric field then is the amount of flux divided by the area that our flux is in, that our flux is passing through, the number of lines passing through that area. Okay, so we have another definition of electric field, and it's this: that our electric field equals, and we're introducing our new unit of capital phi, phi, whichever. Okay, draw an I and an O and superimpose them. Capital I, capital O, superimpose them. Okay, here, I'll make it really big over here. It's that. Okay, yes, the Green Lantern symbol. Okay, as what, deep as darkest night, as light as bright as whatever. Okay. I am so ahead of you. Oh, that's as good here. Hold on. There we go. How's that? That better? Okay. All right. Yes, it does look like a portion of the soccer field. Like, okay. All right. So our electric field then is phi, which is our flux, divided by A, which is our area. Okay. So, or in other words, our flux. In fact, let's make that rule. Flux must be drawn in green. Okay. Flux equals E dot A. Now you may be looking at that and asking yourself, A has a direction? Area has a direction? Yes, it does. Area has direction. Okay, so think about how that for a weaker field, think about how this works. For a weaker field, we have fewer lines per unit area, right? Stronger fields will have more lines per unit area. It's another way of thinking about the line density. The electric field is the line density. Because there's scalar product and vector product. So dot product is also known as scalar product. So when we multiply these two together, we will get a scalar value. Okay, and if it's cross product, then if we multiply those two vectors together, we get a vector value. Does that ring a bell? Hopefully. Okay, the lecture's on video. You might want to go back and look at it. I'm not meaning to be snarky, but that's we've done this. So, all right. So, yes. I apologize for shouting into the microphone. Yes. Area. Area has direction. Okay. This is defined by the magnitude and the direction of the normal vector. Oh. So think about this. If you have this area right here, okay, there is a particular, if it's a uniform area, we'll consider it flat for right now. If there's a uniform area, then there is a particular direction that is unique to that plane, and it is the normal vector. Okay, or we can show you another way. Okay, here's my plane, so there's this surface right here. That is my normal vector, right? So, if you guys remember this from your friction, as this tilts up, okay, in fact, then we zoom out a little bit. Okay, as we tilt this, then our normal vector tilts with, right? Okay, so, or you can do this. You put your palm out, stick your thumb on top of it, and as long as your when this happens, yeah, turkey, right? Turkey. Okay. So your thumb represents the normal vector for the plane of your hand. And it is unique. Now, that is the direction of the normal vector. What do you think the magnitude is? Well, it's how big the area is, right? It's the magnitude of the area. So, all right. So, if phi equals E dot A, right, that means that this also equals E A cosine theta. All right, so area equals, so phi equals E A cosine theta. Okay, so let's draw an electric field here. Okay, if I take a sheet of paper and I hold it here, right? The normal force, the normal vector is that direction, right? Yeah? So if the normal vector is that direction, so there's my paper. There's my normal vector, right? Okay, there's the angle that it's making with the field, right? Okay, so this is going to be EA. Okay, this angle would be 90, right? So E dot A dot cosine of 90, well, cosine of 90 equals 0. And so our flux, the amount of lines passing through that area, equals 0. Now, if we have a second one, okay, so now here's our paper and it's crossing like this. Okay, then our normal vector can be in that direction, right? And we would have E dot A dot cosine 90. That's 1, and so we now have right, 0. That's what I said. Cosine of 0. Cosine of 0, okay, is going to equal 1. So our flux then will be EA. Yeah? Okay, and then you can imagine as this paper is rotating, okay, so if we're here, okay, then our field lines are going to be less than if it was perpendicular to it, right? If it's in the same field. And so as we rotate, then our lines are increasing and decreasing, increasing and decreasing as we go through, right? There is a real world and a really cool application of this. Yes, when you have, let's say that this is a loop of wire, and you rotate a loop of wire through a uniform magnetic field, okay, it will cause an induced current in the field. In fact, okay, it's not electric field. I take it back. It's a magnetic field. There's also such thing as magnetic flux. We'll talk about magnetic field lines later on in the semester. But the idea is a changing magnetic field induces a current in a loop of wire. Well, you can turn the wire in a steady field, and if you turn the wire, it creates regular current, and so it may alternate directions. Okay, but what you've created then is an AC current, an alternating current through your loop, and that's the principle behind electric generators. So, pretty cool stuff. It's amazing real world application, but that we'll get to that at a future time. Okay, so it's area with direction. So we now need to talk about closed surfaces. So we need to draw another field here. Okay, so flux in closed surfaces. I do not often draw my flux symbol neatly. So listen for when I say flux, because if you can't tell that that's flux, then you'll have to listen for it. And yes, the common question is often, okay, when do we start talking about the flux capacitor? There isn't one, don't ask. Okay, so here's our closed surface. We have a box in our electric field, and we have an area on top. We'll call it area 1. Here's area 2, area 3, and area 4. Yeah? Okay, this is a box. Now, we have an electric field passing through the box, and we're going to pay attention to the flux that is passing through the box. Got it? For A1 and A3, both of those sides are parallel with the field lines. Therefore, the flux going through them is going to be 0. Yeah? Okay, yes?
Is the box like 3D or?
Sure.
It's top.
Okay, well, I mean, we can draw that, but we can draw it, but it doesn't illustrate my point any better than this. And I didn't draw a three-dimensional field source either. Okay. So the flux 1 equals flux 2 equals flux 3 equals 0, right? Okay, so those don't really have any factor with what's going on here. Flux 2 is equal to E dot A2 Ray, please quit making those noises with your hands.
What are you doing with your hand, Ray? No. Like your hand is like.
Okay. Flux 2, well, this is cosine. Okay, A2, the normal for A2 is in that direction, so the cosine is going to be 0. Cosine is 0, which is going to be 1. All right? And so the flux is going to equal EA2. Now, by convention, when you have a closed surface, the area vector is pointing away from inside. It points away from the interior. Okay, so the A3 vector is going to be in that direction. A4 vector is in that direction. A1 is in that direction. That makes sense? Okay, it's just by convention that we do that. However, that does have an implication because I4 or flux 4, okay, is E a cosine of 180, because here's the direction of the field, here's the direction of the area, and this all of a sudden becomes negative EA4. Okay, but if all the sides are equal to each other, that means that EA2 and EA4 add up to 0. So, the flux through okay, the flux equals 0 through a closed surface.
So it can be like this way too, but it's 0.
It doesn't matter. So if you drew an amoeba-looking thing, okay. So if we drew, okay, if we drew that, it doesn't matter. That the amount of flux going in is equal to the amount of flux coming out. Okay. There's a more detailed proof in your book of this. I don't want to do it. Okay, the box illustrates what we're talking about just fine, and you guys have calculitic minds, so you guys can see that this example like this will cause, is good enough example. Okay. However, what did we do here? This was 0 and that was 0, and this is EA2 and minus EA4. We added them together, right? You know what that means?
Sum.
It's a sum, and you know what a sum means? An integral. So we have, what really happens is we have phi equals the sum of I equals 1 to 4 of EI dot AI, and this becomes the integral of E dot dA. Now, if we are integrating over a closed surface, this happens enough in math that we have a special symbol for it. The special symbol for it looks like this.
Oh, man.
Yeah, I know. Hold yourselves down. Okay. You know, so some of you new to this culture may not be able to handle this kind of radical drawing here. Okay. So, this then is the definition of our flux. Okay, that this is over a closed surface. So the flux, the amount of flux passing through a closed surface, okay, is equal to the integral of E dot dA.
So it doesn't change?
Well, in a closed surface it equals 0, but if it's not a closed surface, then you still do. Ashmi.
So are we going to ever use that actual equation? And if so, does the circle like change?
We will not use this equation for general purposes. We will use it conceptually, and we will use it, which is a nice thing, and we'll use it for highly symmetrical surfaces. Right. In other words, to make math easy so it doesn't take up your time on your test. Okay? Yes?
So that's only for closed surface or general?
It always equals 0 for closed surface. That is the general form. This is the general form and the definition of flux. And we do show that it can be done over closed surfaces. This does need to be closed.
So that
Okay, it represents that it can be done over a closed surface.
So that circle thing doesn't change the meaning of integral?
No, not really. Okay, well, it's to show that we're doing it over a closed surface. That's the purpose.
Oh,
Okay.
Closed